talk about that as the Doornail, zero-point energy, and the low temperature physics in early quantum theory.
Yes, thank you. I guess that this first slide of mine is a rather famous painting by the British artist Joseph Rideau Darby, who painted it in 1768, and which illustrates the fascination of people at the time of the new air pump and the apparent vacuum that this air pump produced. They noticed, for instance, with some sorrow that this little bird, you could see the bird, so apparently lights of wave can propagate through the vacuum, but they couldn't hear the bird, unfortunately so perhaps. And you may well ask, what has this vacuum to do with the zero-point energy? As I shall argue, it has a lot to do with it, although this can only be seen in retrospective and was completely foreign to the physicists in the early part of the 19th century who introduced this notion. I'm a historian, I'm not a physicist, and I'm not a philosopher. Historians normally proceed their presentations in a strict chronological order, but I'll not do that today. On the contrary, I shall proceed in a reverse chronological order, so to speak. So I will first call attention to some apparently totally irrelevant observations which astronomers and astrophysicists made in the late 1990s when they studied a class of supernova known as supernova 1A, and they studied their spectra, and there were two groups making these very complicated observations, and eventually they agreed with regard to their data, and that posed a problem to cosmology. Because in order to make sense of these observations, they had to conclude that the universe is not expanding. That had been known all the time since the early 1930s, of course, but that it was expanding at an increasing rate. In other words, that it's accelerating. That very important insight dates from about 2000, and it's part of, it's a defining feature of what is known as a standard cosmological model, sometimes a consensus model, and sometimes indeed the lambda CDM model, where lambda stands for the cosmological constant, CDM stands for cold dark matter. And that's a very successful model, but like most other successful models, not without its problems. One of the problems is the dark matter, which is not of relevance today, so I'll just skip it. But the other one is the so-called dark energy. This dark energy is presently believed, at least by the majority of people, to be a manifestation of Einstein's cosmological constant, which he introduced in 1917, and that famous and sometimes infamous cosmological constant is believed to be a manifestation of the quantum processes in the vacuum, the zero-point energy of the vacuum. So there is this close connection. So let me just point out what is well known, of course, that the major part of the energy matter content of the universe is made up of dark energy. Some 70%, as the universe grows older, this percentage will increase and continue to increase. But there is a problem, and a problem which has been recognized for quite some time, and that is this problem. Why is the maximum energy so small? That was a problem which was first recognized to be a problem by the brilliant Russian theorist in 1967. And today it's a big, big problem. And the reason is that if one tries to calculate the energy density of the vacuum according to quantum field theory, one comes up with a number which is ridiculously larger than the one which can be inferred from observations, which was what Steven Weinberg pointed out several years ago. He calls it this enormous difference. He refers to it as the largest discrepancy between theory and observation ever in the history of science. And it's hard to disagree with him. I do not know if that discrepancy has been reconsidered and what the situation is nowadays, but as far as I'm aware, there's still this difficulty between theory and observations. And I'll return to the cosmological constant, but now I want to go back in history, not all the way back to 1911 when the concept of zero-point energy first comes up, but to the magic year of 1925. And the reason why that year is magic is, of course, that it is the birth of quantum mechanics as we know it, contrary to the so-called old quantum theory, which goes back to Planck in 1900, of course. And it's well known that quantum mechanics essentially dates from a seminal paper known as the Umdeutungspaper paper, which Heisenberg wrote in Zeitschrift für Physik in September 1925. And in that famous paper, rather late in the paper, he notices this result. He says that classically, we have for a harmonic oscillator, we have this result, which is not really the classical result, but it's Planck's result, of course. But quantum theoretically, meaning quantum mechanically, we have this additional 1/2 factor. And he points out that this is strange, and that's all he says about it. But still it's important because it's one of the very few potentially attestable consequences of the new quantum mechanics, of which there were very few originally. Now, half a year later, we have a different kind of quantum mechanics, what Schrödinger referred to as undulatorische Mechanik or wave mechanics, and of course, Schrödinger, who was very dissatisfied with the Brownian mechanics, saw that his theory was different from Heisenberg's. And at that time, when he wrote his famous series of papers in Univeristy, I believe in the second of these papers, which was written at a time when he did not yet realize that the two theories are formally equivalent, he had this comment, and that's the very same, he's referring to the same factor here, the zero-point energy at absolute zero temperature. And then he called it, he says that merkwürdigerweise, sorry, how did I read that here? Can you please? Yeah, here it is. I better put that away. Yeah. Merkwürdigerweise, strangely, our quantum labels are exactly the same as in Heisenberg's theory, exclamation mark. A month later, when he had realized that the two theories were equivalent. They were not particularly strange any longer. But then he goes on, and that's a little interesting thing about and the difference between Heisenberg and Schrödinger, that Schrödinger goes on referring to the history of this concept. He realized that it has a history and that it goes way back to Max Planck in 1911, something apparently unknown to Heisenberg. So the concept of zero-point energy is due to Max Planck, not in his original quantum theory of 1900, but in his so-called second quantum theory of 1911, which he defended for about 5 or 6 years, and then the theory was abandoned for various reasons. But there was one element in Planck's second quantum theory which was not abandoned, an isolated part of it, and that was its prediction of that a harmonic oscillator, a material harmonic oscillator has to have this zero-point energy, which, as it says, or rather, to be more exact, it's not a single oscillator, but it's a collection of many oscillators, and then the average energy, which is equal to 1/2 at absolute zero temperature. He expounded this theory at the most famous First Solvay Congress in 1911, and here we have this iconic picture from this Congress with Planck in front of his blackbody radiation law, and we have a number of other celebrities. That is by Carré in a conversation with Helge Kragh. We have Einstein, of course. We have Monsieur Solvay here, and then we have Rutherford and Jeans and others. Planck believed at that time that the theory was correct, and he believed that the zero-point energy was real, but he also realized that it would be very hard to test it experimentally. His second theory and the zero-point prediction from it aroused considerable interest at the time. One of those who took it very seriously and was really excited about it was Einstein. In 1913, where both Einstein and Planck also was at the second Solvay conference, he also gave a presentation of his ideas, and Einstein was quite fascinated about it, and for a while he took it very seriously and even thought that he had found empirical evidence for this mysterious energy, which he did in a paper written with his then assistant Otto Stern. Otto Stern is well known, of course, from the Stern-Gerlach experiment. Later, he became a Nobel laureate, but at this time he was the assistant of Einstein, and that was in Zurich, but shortly before Einstein went to Berlin, I think. And anyway, in this analysis, they consider the specific heat of molecular hydrogen, an ordinary hydrogen gas at low temperature. And then they make calculations based on different assumptions. One assumption that this is a zero-point energy, this is Planck's zero-point energy, and no zero-point energy at all. And they conclude that with some reservations that the experimental data are in better agreement with Planck's zero-point energy. Einstein apparently believed that only very shortly, because a couple of months later he had second thoughts, such as that he confessed in a letter to his friend Paul Ehrenfest, a letter in German, of course, and he described the concept of zero-point energy as mausetot, completely dead or not dead as a doornail. But Einstein, like people were not really sure whether it was a good idea or a bad idea. Most people were undecided, and the reason was, of course, that they waited for experiential evidence which would either reject the prediction or confirm it. So it was a matter of much discussion, not only by Einstein and Planck and so forth, but also from a different angle by Niels Bohr in Copenhagen. Bohr had his own reasons to assume some kind of zero-point energy, not only in his atomic theory. Perhaps I should mention just en passant that Bohr was not at either of the two Soviet conferences, not in 1911 and not in 1913. But in the atomic theory, the classical one from 1930, where if you have an atom in its ground state with the electron revolving at a definite speed around the nucleus, then it will go on revolving with the same velocity, whatever the temperature. The temperature independence, also at a zero absolute temperature, there will be a motion. This is a kind of zero motion, but one very different from Planck's. And that phenomenon, or that prediction, implicit prediction of the Bohr theory, caused some people at the time to question the Bohr model of the atom, because some people argued that it was a paradox, that we can have an electron revolving at absolute temperature, and that is the reason why we should not believe in Bohr's atomic theory. In order to test this prediction, the natural thing was to make experiment at very low temperatures. And low temperature physics, very low temperature physics, by the standards at the time, that meant the famous Leiden laboratory of Helge Kragh, which at that time, and for several years actually, was the only laboratory in the world with liquid helium at this disposal, and we could make these experiments at very low temperatures. And people examined a number of phenomena, radioactivity, isotope composition, and I don't know what, in Leiden, without coming up with any decisive answer whether pro or con. One of the commonly honest assistants, Wilhelm Kesum, made experiments which he interpreted in favor of the zero-point energy hypothesis, but they were not very convincing, and so still in 1920 the whole matter was undecided. It didn't last long though, because in September 1924, a young American physical chemist, Mulliken, who much later received the Nobel Prize, not in physics but in chemistry, because of his contribution to quantum chemistry, he made very detailed examinations, not at low temperature, but he compared the two molecular spectrum of the diatomic molecule boron oxide and the two different boron isotopes, vibrational spectrum and rotational spectrum, and he came up with results from which it appeared rather unambiguously that there is a zero-point energy of this molecule. It's a little interesting that he published these results first in the fall of 1925, and later in the early spring of 1925, a large article in Physical Review. The reason why this is a little interesting is that at that time we had a situation in quantum theory often referred to as the quantum crisis. the old quantum theory was in trouble, but the new quantum mechanics had not yet come into existence. And in this whole situation and crisis, this could have played a role, but it did not. The physicists apparently simply were unknown about Mulliken's result, although he stated it very clearly. Bohr was unaware of it, there's no doubt about that. And when Heisenberg wrote his article, and when Schrödinger wrote his article, they didn't mention that the zero-point energy had in fact been established by means of these experiments. Now, go back to to proceed with the issue of the vacuum. There were people in the early part of the 20th century who realized, or rather hypothesized, that the vacuum is full of energy. That hypothesis, which is considered a fact today, of course, was also stated in an entirely different framework, namely within the framework of ether theory. Classical, which means electromagnetic ether theory, which was at that time, in the early part of the 20th century, the dominant theory among physicists. And I don't have to point out, I guess I hope that the ether did not die in 1905 with Einstein. It lived happily on, at least for a decade. One of those who didn't question the ether, far from, was a big physicist, Oliver Lodge, very important person in this business. And in a paper in 1907 in Handbook magazine, he has this wonderful conclusion. He calculates the energy density of the ether, which other people will call the vacuum. And you come up with this enormous amount of energy, or the energy density, which he expresses in a nice language, I think. But still, I mean, he belonged to the past, and but there is some continuity, because not so many years later we have another physicist who was one of the pioneers really of quantum theory, who nourished somewhat similar ideas. I already mentioned, I think, Niels, he was also on this picture from the 1911 Congress. It was actually announced who was the prime mover behind this Congress. Niels was a physical chemist, also a Nobel Prize laureate, and he was very important in the early development of quantum theory. In spite of being a modernist in this sense, he believed in the ether. He died in 1940, and he never questioned the existence of an ether. At that time, during World War I and the years after, Niels did more or less the same as Lodge did, namely he calculated the energy of the ether, or for that matter, the vacuum. But he did it by taking quantum theory into account. And he too came up with a very large figure, not quite as large as Lodge's, but certainly very large, and you see there is quantum theory all over. This theory of Niels, in part for external reasons, the war and the followed after the war, his works were not well known, certainly not outside Germany. They were known, at least to some German physicists, one of them being Wilhelm Lenz, yes, who sort of tested Niels' hypothesis by applying it cosmologically, which in itself was is interesting. He said, if the entire universe is filled with zero-point energy, and the universe he was thinking about, that was the closed Einstein static model of the universe with a definite volume, and then he concludes that then the energy due to that zero-point energy would be so large that the universe would shrink enormously. And so he concludes that there probably is no zero-point energy in vacuum, I mean due to radiation only. I can see that, yes, and that was the standard view at the time in the late 1920s. Leading quantum theories such as Pauli and Jordan, Einstein too for that matter, were sure that there is no such thing as zero-point energy in the free radiation field. And to the road towards dark energy has two routes, quite distinct, and they can only see to have these two routes retrospectively, of course. One is the zero-point energy route, and the other is the cosmological constant route. And the two routes were essentially the same, was only realized much later. So I want just to return to the cosmological constant, point out that it was part of Einstein's cosmological field equation in 1917. Einstein eventually abandoned it for various reasons, but a different story. But Georges Lemaitre, the famous, I hope he's famous, Belgian physicist and the true inventor of the expanding universe, in 1934 he explained very clearly that the physical meaning of the cosmological constant is an energy density of the vacuum. That paper, many of these papers have their own stories, and this is hailed today to be one of the founding papers of dark energy physics, and for good reasons. At the time, it was neglected, purely. Lemaitre himself never referred to it. I had looked for citations in the 1930s and come up with around zero. Nobody simply referred to it. So it took a very long time, and indeed to the 1960s, before the first people, and I mentioned Sadovich, and he was the first one who made this combination, noticing that the quantum prediction resulted in a much higher result than the observations, which will later be confirmed, and apparently is a problem which is still with us. Thank you for your attention.
I would like to make a remark and maybe complete some of your points. That, the first is that you wrote that QFT predicts very high vacuum energy, and in fact QFT predicts infinite energy density, and the big numbers you mentioned are predicted from modifications of the QFT introducing at hand the cutoff. So you can introduce the cutoff that you want, and so you get the energy density that you want, and this has absolutely no physical basis. And the related point is also that Lemaitre made this analogy as a pure mathematical analogy, and this was resulting from Lorentz symmetry arguments concerning the vacuum. But this doesn't work in a space-time which is not negative. So this analogy cannot be used to justify the acceleration of the expansion of the universe. And my last point is that this acceleration, so there are very interesting proposals to resolve the problem by claiming that what gravitates in quantum physics is not energy, but another quantity. This will be part of the subject of my talk this afternoon. And just to finish, the problem, the so-called problem of cosmological constant is perfectly solved at present by the gravitational cosmological constant introduced by Einstein. But I will speak about that this afternoon.
I mean, I know that there are different views, because in no way proven that the dark energy, so to speak, so the acceleration of the universe is an observational fact. But it is not in the same manner a fact that what makes the universe blow up is the cosmological constant. There are other ideas, including a kind of constant which is not a constant but varies in time. Phantom energy is one.
For mathematical constancy reasons, the cosmological constant, the true cosmological constant cannot vary in time.
No.
So, be sure and
Your first slide was the slide that shows the discrepancy between the prediction of the Big Bang model and this acceleration of expansion of the universe. And then you mentioned dark energy as a solution to this problem. But can it be imagined that this mysterious dark energy is an ad hoc hypothesis to save the Big Bang theory?
Yes. No, that's completely wrong. I mean, all these models, whether including dark energy or not, are Big Bang models. All the models which are shown on this are Big Bang models in the sense that
I agree with that.
there is a beginning of the universe.
I agree. It's
So
very.
no one.
It's taboo to think that the Big Bang model could be wrong. However, the Big Bang model has this immense problem that you mentioned of the discrepancy between density of energy
That is
and
not a
120
problem
orders
of the
of
Big Bang
magnitude.
model. That is only a problem of the Lambda CDM.
Come on.
So, Simon, do you want to ask a question? Or
Maybe
so,
Mark, you can
thank you.